The next method in the procedures of slices is the simplified Bishop procedure. It's slightly more complicated than the ordinary method of slices. It makes the assumption that the interslice forces all are horizontal. So there's no shear on those interfaces, only normal stresses. And what we'll do now is sum up forces in the z direction. And so you get n cosine alpha plus t sine alpha minus w is equal to 0. And so we can then substitute in, our expression for T. It's the shear strength times delta L divided by F. And so we plug in our more Coulomb expression here for S and multiply through by delta L. And I'm including a pore pressure in here now, just so that it's a more general formulation. If you want to solve the problem without pore pressure, you just set it always equal to 0, and you can do a total stress analysis, no problem. So what we'll do is take this equation and solve for, well, we'll substitute this in here for T, and then we'll solve for N. And we get an equation for N that is quite a bit more complicated than what we had for the ordinary method of slices. The normal force now depends on the factor of safety. All right, so what we're trying to do is solve for n so that we can compute the factor of safety, and now we have an expression for n that depends on factor of safety. So what we'll find is that we end up with an implicit equation, and we can't isolate factor of safety. We have to do iterations to get it right. So anyway, now that we've got n, we can compute sigma prime, n over delta L minus u, and then we can plug that in to our equation for the procedures of slices. And once we plug in sigma prime, we get this equation right here for factor of safety. I won't read through all the terms, but I will point out that that there is a factor of safety that appears down here and there, and it's not really configured in a way that you can somehow isolate that factor of safety to the side. So anyway, what you'll do is first make a guess at what the factor of safety is. Maybe you guess it's 1.5, which is usually the regulatory requirement we need to meet. Then you can calculate factor of safety, and maybe you get 2.7. Well, then you can update it and put in 2.7, and then you might compute 2.81. Then you put in 2.81, and then maybe you compute 2.82. It doesn't take very many iterations to converge and find compatibility between these assumed and the computed factors of safety. If U is equal to 0, or you're doing a total stress analysis, it simplifies the expression shown right there. A little simpler to solve. All right, so the equation for F is implicit and iterations are required. Okay, so I've done that for this previous problem, illustrated right here, that we did for the, sorry, I should have circled that too, for the ordinary method of slices. Now we're going to solve it using the simplified Bishop procedure. And by iterating, I found that the factor of safety is 4.154. And it only took me about 3 iterations to get that result. So I'm not illustrating how I did that. We can talk about it during one of the live sessions if you want. But now I have a little table that summarizes the final outcome after doing those iterations. There's slice number, here's the weights, alpha, those are all inputs. Okay, the value of n now depends on the factor of safety, and so this is where we've gotten these normal forces after doing iterations. And then the t values are summarized in the table right here. Notice these t's are all positive. That means that they're all acting from left to right to provide resistance to the slope. I don't know if I showed it before. I may have not pointed this out, but for the ordinary method of slices, slice 1 actually has a negative t, which means that it's acting in this direction instead. And that's because we assume there were no forces there. So this slice would actually fail in the down to the right direction. Doesn't make a lot of sense. Okay. Then we can compute again the resultant force in the z and x directions. And once again, you get zeros in the z direction. So it does satisfy vertical force equilibrium. but you get an imbalance in the x direction forces, and the sum of those forces comes out to be 158 kilonewtons per meter. It should actually be 0. Right? So if a method of slices works, you should get the sum of forces 0 in both directions. So we can't get force equilibrium by constraining the forces to only be horizontal. It just doesn't quite work out that way. So the simplified Bishop procedure also does not quite provide us with equilibrium. Now, one thing I wanted to do, though, is now that we're assuming that there are inner slice forces, now that we know N and T for each slice, and of course we know W, we can now compute those interslice forces too. So here's how to do it. You start with slice 1. We have N1 and T1 and W1, and then of course there's only E1 acting horizontally on the side. So E1 comes out to be 58.5 kilonewtons per meter. Then we can move on to slice 2, and you have E1 acting horizontally here. Then we know W2, T2, and N2, and we can compute E2, and it comes out to be 96.7 kilonewtons per meter. So we've actually solved for the interslice forces here. Another thing you can do with those interslice forces is compute their resultant. Since they're both horizontal, you can just represent them with a resultant force QI that's acting at some height that would account for the difference in height between E1 and E2 so that you still have moment equilibrium. And notice if you sum moments about this point right here, right, W2, T2, and N2 all act through the center point, so there are no moments arising from those forces. Therefore, E1 and E2 also must be configured at heights that result in 0 moment acting about the base. And so what you'll find is that if you represent the difference as a resultant Q, that resultant has to act through the bottom of the slice as well. In this case, E2 is bigger than E1, so we would actually have the case that E1 is acting at a higher position than E2 in order to produce 0 moment about the base. So anyway, if we come up with those resultant forces for each slice, for slice 1 it's just equal to E1, right, minus 58.5, because it's acting to the right to left. For slice 2, it's going to be E2 minus E1, which comes out to be 38.2, and then for slice 3, the force is acting from left to right, so it's positive 96.7. Okay, then we can add together all of those forces, and it's equal to 76.4 kilonewtons per meter. These should all be kilonewtons per meter. So if we did have force equilibrium, the sum of all of those forces would have to be 0, right? All of the interslice forces would have to, interslice force resultants would all have to add up to be 0. So that's another indication that the simplified Bishop procedure does not satisfy equilibrium.